Good morning, everyone. We come to lecture number 8. Okay. So last time we talked about the band structure of monolayer MOS2. So we basically use a two-band model. Let's briefly review what we have done last time. We use a two-band KP K dot P Hamiltonian. Actually, we derive it Hamiltonian for monolayer MOS2. The Hamiltonian is something like this. There's a parameter. I mean, in the PIL paper, they use AT to represent it. Okay. And then we have tau denotes the valley index, and then kx sigma x plus ky sigma y, and plus delta over 2 sigma z. Okay, so the wave function has two components. You can say A and B. So the A component corresponds to the orbit in d z square. So this is the m equal to 0 orbit, and this one corresponds to dx square minus y square minus d. I forgot. Okay, let me look at the PowerPoint. Yeah, dxy. Okay, dxy. This is plus I tau. So this corresponds to m equal to plus or minus 2. Okay, so here, why do we use this combination? Why this combination? The reason is because we calculate near the k plus minus k points, and which have the threefold rotational symmetry. Let's see. So this threefold rotational symmetry, so this makes LZ a good quantum number. Okay, so that's why we use m equal to 0, m plus minus 2. Okay, so that's the reason why we can set this basis. Okay, so this is what we did last time. But generally, like including points away from k points, we need to use dx and dy as separately as as basis. Okay. So once you are away from the k point, then this LZ is no longer a good quantum number. So it's not good to just use this combination. So you need to generally use these two as basis. Okay. So the Hamiltonian So the Hamiltonian will be a 3x3 matrix. Hamiltonian will be 3x3 matrix. It will be a 3x3 matrix. So this 2x2 matrix is only good near the K point. When you're away from the K point, then you use a Hamiltonian that is 3x3. So you basically have a Hamiltonian that is x1, 2, 2, x3, 3. Then you have 1, 2, 1, 3, 2, 3, 2, 1, 3, 1, 3, 2. So this will correspond to you can say A, B, C. So this will be the D Z square orbit. This will be this orbit, and this will be the XY orbit. Of course, when I say orbit, they are actually all one-line states. That means you need to sum over all the sides with the plane wave factor there. Okay, so these are all plane wave. So you should actually name them like this. You should more accurately. You should make them like this. You should use a sigma. So what does it mean? Each of this is a linear combination. It's a linear combination of E, I, K, R, and then times a localized wave function. So each of this is a one-line function for each of this. So basically you have this 3 set. You just you just use this copy. And then similarly, okay, so these are the 3 basis function. Functions. Okay, then you have a 3x3 matrix. So how do we calculate this 3x3 matrix? Generally, you can use a time binding model. To calculate this Hamiltonian is a 3x3 matrix. Okay. So I'm not going to go through the details of this model. I mean, I don't know the details. So I just show you the paper. People have done it. Okay. So this paper has done the calculation. So this is the paper from a Dichalcogenides group. He was in Carnegie Mellon. Now he moved to University of Washington. Okay, so that was the work 10 years ago. Okay, so this is a 3-band time binding model for monolayer TMD. So why is it called 3-band? The 3-band means this 3. Okay, these are the 3-band. Okay, you consider 3 orbits, and then construct a 3x3 Hamiltonian. Okay, so in this paper, they use the time binding model. Okay, so let me briefly go through it. So this is the set, the first band, second one, the third one. This is what I showed you before. These 3 are the major ones. Then this is the Hamiltonian they set. He used a small h. but you get the meaning. 3 by 3. Okay, so these are there are totally 6 independent elements because these 3 are just complex conjugate of the other 3. Okay, there are 6 of them. So these are the 6. 1, 2, 3, 4, 5, 6. Okay, so these are the elements. And then inside you have this T, which this T are just hopping. The hopping parameter. So these are all hopping. So you define the E. The E is defined here. The E is defined here. So you can see they're hopping. Like R is one side. R minus this R is the near side. Okay, so these are just the hopping energy among the 2 sides. They can be the nearest neighbor or the next nearest neighbor, or I mean whatever. But they're not in the same site. But they're, of course, they're all R1. Okay, R1 is how far away the neighbor is. Okay, so once you calculate this hopping energy, then you can use, these are the results, how they calculate it. So this alpha and beta are just the vector. Okay, these are the K. These are our general K over the whole brilliant zone. Okay, so these are basically the result they got. So these are all going to use them as fitting parameter to fit the DFT result. Okay, to fit the DFT result. So they have 2 steps. One is use the nearest neighbor coupling. Just use the adjacent one. So like what you see here, only consider this one. This is the nearest neighbor coupling. Only these 6 of them. Each of them has 6 of them. Okay. Then if they use only the nearest neighbor coupling, then they get the result. Okay, so let me show the result to you. So this is the result with the nearest neighbor time binding model. I mean, these are different TMDs. Okay, you can see this different material. So let's just focus on MOS2. Okay. I mean, this GGA, LDA, they're just different methods in a DFT, like different approximation. Okay, so this red dots here, these red dots are the DFT results, which is supposed to be reasonably accurate. Okay, so the blue lines are the time binding model with only the nearest neighbor coupling. So they just adjust the parameter to best fit. Okay, you can see that the fit are not very good. But when you are near the symmetry point, near the K point, it is good. Okay. Of course, we use a 2-band Hamiltonian. We can already describe near the K point pretty well. Okay, so now they use a 3 by 3 matrix Hamiltonian. Then you will expect that the K value description is still good. And near the gamma point is still okay because these are high symmetry points, and usually the high symmetry points are easier to deal with. But once you're away from the K point, you can see that they are very off. Okay, they're very off. So that means the nearest neighbor coupling is still not very good to describe the whole band structure. Okay, is that okay? So that's what they did. Okay, now they have a model. Also calculating this 3 by 3. They use a different symbol V. Still 3 by 3, but it is the 3rd nearest neighbor hopping. That means you include up to 3. Okay, hop 3 times. Then you have a more detailed calculation. Then these are the expression. You can see the expression are significantly longer, right, than this one. This is already long, but this is even lengthy, more lengthy than that. Okay, so these are all the results, and these are the fitting parameters. This is for nearest neighbor time binding model. Okay, this FP means first principle band structure calculation. So these are the number that they fit. Okay, so basically you use this expression, use this number, you plug it in, then you're supposed to reproduce these blue lines in your computer. Okay, if you want to use the model for your analytical calculation, then you just use this number, use this expression, then you can just plot it out. Okay, so and then for the third nearest neighbor coupling, then they have also the result here, and then these are the numbers. Okay, you can see many more numbers, and these are all different materials that they use to fit. Okay, so suppose you want to do a modeling on a monolayer WS2, and you want to use a time binding model to calculate, then you can just get all these parameters. Okay, these different parameters. Actually, these are two lines of parameters. Okay, two lines of parameters, and then this is the result of the third nearest neighbor time binding model. So you can see that. Let's focus on MOS2 then. Okay, so you can see that it's actually pretty good. When you include up to third nearest neighbor coupling, you can describe the whole brilliant zone pretty well, including the Q values. Okay, so if you want to have an analytical result, like on your band structure, then you can just get those numbers. You can replot this in your computer, and let's say you want to get the effective mass of the Q value. Once you have the data in your computer, then you can calculate the curvature. Then you can get. I mean, as long as you have the band structure, you can calculate different parts. Okay, so it's just a 3x3 matrix with all the number that you need are all included. Okay, so they provided those basic parameters, and they're pretty good, because for DFT is just some number, like I would say DFT is just like for me, I feel like a black box. You just calculate and show the result. But for time binding model, there are more analytical content. It's a 3x3 matrix that you can deal with. Okay, so this one I don't think they include the spins or spin orbit coupling. Okay, so yeah, so this is the result. I mean, here they have the spin orbit coupling. Okay, which I'm going to briefly talk about. Okay, when you have the spin orbit coupling, this is the with the spin orbit coupling. Okay, then they have more results. Okay, so any questions before we move on? Okay, if no, then let's go ahead. We are going to talk about the band structure with the spin. Okay, with the spin. So first, this is the result that with the participation of the orbit. Okay, and let's talk about the spin, and then we'll come back to here. So spin orbit coupling, according to what we did last time, okay, last time we from the Dirac equation we derived the Hamiltonian of the spin orbit coupling. Okay, so this is Dichalcogenides paper, PRB paper. Okay, so then we talk about the spin orbit coupling, how it affects the band structure. So last time from the Dirac equation, in the non-relativistic limit of the Dirac equation, we got the spin orbit coupling Hamiltonian, which is this sigma dot E cross P. And then I talk about two cases. One is the Rashba spin orbit coupling. The other is the spin orbit coupling in the atoms with the centrally symmetric potential. So for that case, you can change it into, okay, let's change this sigma into spin. So this one change into spin because A is equal to this. Okay, so sigma is 2 over h s. So when you plug it in, you have a 2m s, and then the electric field is basically negative 1 over r. I
think there's no H bar.
There is. Sorry. There's no H bar here. Yeah, there's no H bar here. Okay, so for the electric field, this is the derivative of r, and then along the r direction. So you can put it like this. Then after you put it in, I mean we already got this before, but just do it again so that you know that we're going from the Dirac equation. So this is the L, okay? So this one you can treat it as a parameter alpha. So eventually it will be alpha S dot L. So this is spin-off decoupling. So you need to know that alpha depends on the screening. Because this V overall is the mean field potential. So V is the this should be just a R, is the average potential. I mean you can use mean field then. Mean field basically means the average. Mean means the average field of the atom. So when you have more electrons, then this is no longer 1 over r Coulomb potential. It will be somewhat modified. Okay. So and eventually you give alpha. So now we just treat alpha as a parameter. Okay. So this one, once you are in an atom, okay, let's say you are in the MO atom, which is spherically symmetric, then there's no particular direction that is favorable. You just need to include because alpha S dot has 3 terms. Has y. So all these 3 directions, they are equal. There's no one direction that is like particularly good when it is spherically symmetric. But however, once you put the MO atom in this trigonal let me see. Let me draw the last time we talked about this this thing. Okay, you put it in the trigonal prism of this SE atom. Once you put it in such an environment, so this will favor one direction. Okay, will favor one direction. Let's define this direction as the Z, because this trigonal prism give you the mirror symmetry. Okay, the inference of the trigonal prism of SC atoms will split the d orbits into 3 of them, d, z, and then this one will be the I need to go back to the PowerPoint. Okay. These two, okay. dxy, dyz, and dxz. So these are basically the ML equal to plus and minus 1, plus and minus 2. So you have 3 levels separated. Okay, so this is because of the trigonal prism. So once you have this, then the direction is favor, because which direction is good is determined by the energy scale of the splitting. Because spin-orbit coupling is a small perturbation. Okay, if you just look at the spin-orbit coupling by itself, x, y, z direction, they're all the same. Okay, however, once your atom has a preferred direction with a very large energy splitting, then the spin will only become, spin-orbit coupling will only become a perturbation on this level. Okay, so each of this level is going to split. Okay, let me do it like this. I can do the, okay, plus and minus 1. So each of this is going to, let me just draw one line. So these are twofold degenerate. Okay. So in principle, you have spin up and down here, because you have 2 spin, right? Then the spin-orbit coupling is going to split them. It's going to split them. Now, spin-orbit coupling will only give you tens or hundreds of milli eV. However, last time we already see that the gap between them is in the order of eV. Okay, so let me separate them more. So this one is in the order of 1 eV. Is in the order of 1 eV. And this one is in the order of tens or 100 milli eV. I'm not going to differentiate them. Of course, depends. This one has 0. Okay, I should not call this. This is 0. This is almost 0. 0. Let me not split it then. It's 0. Okay. Okay. Okay, so once you determine this is the z direction, then this particular term will be important. Okay, this term is more important than the other two, because you determine this. Just like when you study Zeeman effect, once you apply a strong magnetic field in one direction, then you pick the direction as the z direction. Okay, then when you analyze the spin, you use that particular direction and the spin up and down. as the basis. Okay. So let's change this into a different way. Okay. So let's define the raising operator Lx plus and minus I Ly, and the spin raising operator L Sx plus and minus Sy. So what this did is you apply it on a eigenstate. Let's say you apply this on an eigenstate of m equal to 0 on m. Okay. Then you'll get m plus or minus 1. Okay. Of course, there's a normalization factor. Okay, a normalization factor. The same for this one. The spin z, you get spin z plus or minus 1. Okay, so this is the raising and raising and lowering operator. Okay. So let's calculate this thing. Okay, let's calculate this combination. So what does it mean? This means that you are going to have Lx plus Ly. The meaning of this operator is that you lower the spin by 1 unit, you increase the orbital spin, orbital angular momentum by another unit. So you flip the spin and change the angular momentum to the orbit. Here, you increase the spin and lower the orbital angular momentum by 1 unit. So there's a exchange, a transfer of angular momentum between the orbital motion and the spin. So these are represented by these two operators. Okay. So Sx minus Sy this I should be let me put it here. Okay, so this is the I plus Lx minus ILy, Lx Sx plus I Sy. Okay, then let's expand them. Lx Sx and then minus I Lx Sy Ly Sx. You just so this I and this minus I will become 1. Okay, so this is one term. The second term is Lx Sx Lx Sy minus Ly Sx Ly Sy. Okay, so then wait, I forgot the normalization factor. So this 1/2 square. So when you have 2 of them together, then you just get 1/2. You just get 1/2. Okay, so eventually you just get everything 1/2. Okay, so now you can already do some cancellation. Let me see. This one and this one we cancel, and then this one and this one we cancel. Okay, And these two are the same. Okay. And these two are also the same. Okay. So eventually you get 1/2. You have 2 Lx Sx. And here these two are the same. Then you have 2 Ly Sy. So you have Lx plus Ly. Okay, so you see, so what the result is just this equal to alpha Az Az Lz Sx Lx Sy Ly, then and then plus this copy. Okay, so now you change into this form. Okay, so this is the spin-orbit coupling that we separate it into two parts. Okay, so let me copy this. So let's analyze this term. Let's analyze this term. This is what we call the spin conserving term. Conserving term. And these are the spin flipping term. Flipping term. Okay, so this spin-orbit coupling Hamiltonian has one part. This part directly just give you the splitting, because this one will give you plus and minus m. Okay, this one will give you the splitting. This one give the spin up down splitting. So for example, let me I have to let me just copy this whole thing then. Okay, let me copy this whole thing. So here before, when you don't have any spin-orbit coupling, then the spin will not give you any energy. So spin up or down, it doesn't matter. They're all included. But once you include the spin-orbit coupling, this term is going to so this Az Lz, they will equal to what? This is determined by m, right? This is m. So you will have a spin up is h bar. So this is h bar, and then this is mh. So you have a splitting of m over 2h bar square. So okay, I give you the splitting. Yeah, give you the splitting. Splitting. So that means spin up and down, they will be different. Okay. This m plus and minus 1 here, you need to know they're in different values. Okay, they're in different values. So let me just use 1 first. Let me remove the negative sign. Okay, I don't want to make it complicated. Okay, plus first, and then you have a spin up. This will be plus and minus. Okay, then you have a spin up, spin down, and spin up and spin down, and this gap will be m over 2h bar times alpha. Okay, so this is in one valley, and then in the other valley, you're going to flip it. In the other valley, you're going to have negative. You're going to have negative. Then all this will be flipped. Flip. And let me use a different color then. Okay. So this one, up, down, up, down. Okay, so this is let's say this is the K valley. This is the K prime valley. So you're going to have this splitting, spin up and down. So this is when you only consider this term. This is a spin conserving term. Okay, so why do we separate them? So let's before we go to the spin flipping term, so let's consider when you have a band structure, the transformation of the wave function. Okay, suppose you have an inversion symmetry. Then let's say you have a wave function spin up at the K point. So if you have an inversion operation, so what you would do is you're going to K is a vector. It will become negative K. Negative K. However, the spin does not change. Why the spin does not change? Can anyone tell me why does the inversion does not change the spin? Can some of you explain to me why? I mean, K is easy. K is a vector, so you have inversion. X, Y, Z become negative X, negative Y, negative Z. So of course the K, you have X, Y, Z. Now it become like this. Negative X. So everything about the vector will get flipped. Okay, this part is why does the spin does not flip under inversion symmetry? Now let's not consider time reversal. Why does the spin does not change under inversion? Can someone explain to me why? Yeah. I mean, it's a pseudo vector. Yeah, that's true. Any more pictorial way to explain it? Yeah, it's a rotation. So let's go through it. Okay. Let's say you have a rotation like this. Yeah. You have a rotation like this. Okay. So let's say this is the center. Everything get reverted. Then Then this arrow go to here. This one go to here. So the arrow go from here to here, right? So let's say there's a point here, then this point will go to here. Okay. So let me just draw the point. This point go to here. So this blue to red to purple to arrow. So you just draw it out. Blue to red to purple. Yeah. Blue to red to purple, and then to the arrow. Okay. So this go one round. So this will go one round. So you see that these two rotations are exactly the same, right? I mean, this is a pictorial way to visualize it. You have a rotation like this. You map each this point to the inverted part. You get exactly the same rotation. Okay. I mean, we're not using any like fancy terms like a pseudo spin, a pseudo vector, those things. You just draw it pictorially. You have a rotation. Every point go to the negative part, then you get exactly the same rotation. If you want to use a more algebraic way, then angular momentum is R cross P. So when you have inversion, each of this vector will become negative. Then you just have the same thing. But for spin, you cannot write it as R dot P. I mean, spin is kind of angular momentum. Okay. So if you really want to prove it for spin, then you have to use the rotational operator on the spin. Okay, then it will involve more algebra, but the result is the same. But personally, I just find this rotation picture is just the easiest way to understand. Right? Anything that can be represented by a picture is better than by representing by algebra. So I just think this is a better way. It's a simple way. Okay, so this we explain this. Okay, so now when your Hamiltonian has the inversion symmetry, so this two will have the same energy. Okay, this is just the inversion operator. But let's say the inversion operator is this. You have a Hamiltonian. Okay, you have an inversion. Let's say I inversion. What's the name of operator of inversion? Okay, you use sigma then. Okay, people use sigma to represent inversion. Let's say this is a sigma. If people use sigma I think I means inversion. But we already use a symbol. Okay, sigma I then. Okay, I means inversion. So let's say you have an operator. Let's say operator of inversion, sigma. Okay. So your Hamiltonian is inversion. So will be the same. Yeah. So this is the operation of Hamiltonian is the same. Then, so when your Hamiltonian apply on here, I mean, I'm doing some like a elementary group theory of quantum mechanics. Okay. When you apply on here, you get an energy on here. Copy. Okay. So now you apply this operator. I think this one is here. Okay. you apply on here. O means operator, sigma I, and then you have an operator. These two together, it would just give you 1. Okay, so here you have a O. This is a number. Okay, this is a number. So you can just reverse it. Okay, you just reverse it. Okay, it's a number, right? So you can always reverse it. And this one is just the Hamiltonian is the same. Okay, when you apply operation on the matrix, you have to do it in this way. Like you have one on here, the other on here. Let's sandwich it. That is how the matrix transform under operation. When you apply on the vector, then you just apply on one side. Okay. When you apply on the state, only apply one on one side. When you apply on the operator, the Hamiltonian, then you have 2 of them. This is how they transform. Okay. So what is this? This is the operation. We already did it, right? So when you apply on it, then you have this. Okay. The same for here. The same for here. So eventually, you get something like this. Yeah. Eventually, you have this. You have this. You have this together. You have a Hamiltonian apply on here. Then you equal. Okay, but what is this? This is just equal to the energy of this state. Okay, I mean, this is a Hamiltonian, this is eigenstate. Okay, this is just equal to. So the result is that these two must be the same. Let me use a red color. So these two, you compare this one and this one, then you get the result. You obtain this. Okay, so that means once you have the inversion symmetry, when you go to the other part of the K, you have the same for both, and the spin does not change. Okay, so this is the result of the inversion symmetry in the band structure. So that means when you have the K value here, and then you have a negative K, so this is spin up, you have exactly the same thing as spin up. If this is spin down, you have exactly the same. You flip the K to another value, but the spin does not change, and you have exactly the same band with the same spin on the opposite value when you have the inversion symmetry. And this is the case in bilayer MOS2. Okay, because it has the inversion symmetry. So in monolayer, you don't have this because this is due to inversion symmetry. Is that okay? Okay, so now let's consider another case. They're very similar. Okay, let's consider time reversal symmetry. Let's consider time reversal symmetry. Time. Now, time reversal symmetry is overall more general than inversion symmetry. Time reversal symmetry, as long as you don't have a magnetic field or your material is not magnetic, then you have time reversal symmetry, because all the physical rules, they are time reversal. Generally, all the rules in physics, they have time reversal symmetry. The only exception is the second law of thermodynamics. The entropy always increases. That defines the direction of time. But let's say Schrodinger equation, Maxwell equation, if you flip the time from t to negative t, the equation still holds. So microscopically, all the microscopic processes, that the time reversal. So time reversal symmetry is very general. However, if you already have a magnetic field fixed, then the particle will either this way, when you go, if you have a magnetic field like this, then the particle will move like this. When you go back, you won't go back like this. When you go back, you'll go back like this. So once you have the magnetic field, then the motion is no longer time reversal. Okay, so the magnetic field breaks the time reversal symmetry. So there's a general, general knowledge in condensed matter. But MOS2 is not a magnetic material, and we have not applied magnetic field yet. So it has time reversal symmetry. It's very general. So for condensed matter, as long as you're not dealing with anything related to magnetism, it has time reversal symmetry. Okay. Okay, so but of course, all the magnetic fields are produced by spin or by current. If you also reverse the spin and reverse those current, the magnetic field will also reverse. Then the whole thing will become reversed. So here, when I say apply magnetic field, I mean those magnetic field does not change. It's something external. Then the system will no longer have time reversal symmetry. Okay, so K is a momentum. K is a momentum like wave vector. So when your particle is moving in one direction, so the time reversal is basically you have an operation of time reversal. Then you just go backward. Okay. I mean, I think you already learned this. Okay. But since I want to make the contrast, so let's review it together. However, you have a spin. Okay, this time the spin is like this. You're making a rotation. This time is easy because you're rotating. So what's the time reversal process? Then you have you just need to go backward. Okay, so time reversal will become like this. So that means spin up will become spin down. So this part, you also have this for spatial inversion. But the different thing about time reversal is that even the rotation will be reversed. So the spin will flip. Okay, so here, this part will flip. Spin flips. Flip. Okay. So once a system has time reversal symmetry, then you just follow exactly the same thing. Okay, we just copy this whole thing and then okay, I like this copy and paste function. Very, very handy. Okay, let's just copy this whole thing. Then all you need to do is to change the name. Change the name. Change the name into time reversal. Then time reversal. Time reversal. Time reversal. Okay. So the Hamiltonian is your system. When you don't have a magnetic field, you the same. And this one, now the spin need to flip. This one will flip. This one will flip. The spin will flip. The spin will flip. This is the original one. Okay, so this is time reversal. Okay, so then you have this equation. Okay. Then you have this thing. Now this flip, go down. Okay, so this one, what is this? This is just spin down. Okay, this is spin down. So what you have is I will still copy and paste them. So eventually you copy this. Then here, what you will have is negative spin. That means once you go to the other valley, the spin will flip. Let me use a different color then. Then okay. Okay. So okay, in monolayer, MOS2, we have time reversal. Reversal. But no inversion symmetry. If you want it more symmetric in name, you can call it spatial inversion. Time reversal, spatial inversion. Okay, no spatial inversion symmetry. So this one does not hold. Okay, so this one does not hold, and this one is there. So you never have. You can make it look better. You never have this. You never have this. Okay, this one does not hold. This one will hold. Okay, for bilayer you have both. In bilayer you have both. Okay. In bilayer, we have and we have both. Okay, so you have both of them. So in bilayer you just get both of them. Okay, so you just get both of them. Then you just sum them together. I mean, probably for some of you it's quite basic. So but I think for the new student, they don't know about this yet. Okay, so basically you for bilayer, this one sum over of this, then what you will get is you get this one in K, and then this one you just overlay them. you just get spin. Sorry, I think I draw it wrong. This the spin up and down is wrong. Okay, sorry. This spin. Okay, this is spin up. This spin down. Okay. I changed the color, but didn't change the spin. Okay, sorry for the mistake. Okay. Okay, so this is down. Down. Let me. Okay, down. Then it's up. Okay. So this is up. This is down. Okay, so you have this and this together. Sum over. Then what you will have is, if you have down, and then you have down, and you will have up. Okay, so basically for a bilayer, you get in one valley both spin and they are degenerate. Okay, so in bilayer you have two copies of them. In monolayer you only get one. You only get this. You don't have the other. So that's why when I consider this spin conserving term here, okay, when I consider this, I only need to consider one part. Okay. It's the same for this. This is also a kind of angular momentum. If you do everything that I did with the M, I don't want to repeat it, but if you do all the same thing here, you change this into M. So if you change this into M, then this will be negative M. Okay. So in one K value you have a M, the other value you have a negative M. The same thing. You just do the same thing and change the symbol from the spin to M. So that's why in one value you only need to consider one M, not the other. So in the K value, we only consider plus 2M. There's no negative 2M. Negative 2M is on the other value. So here, once this M is fixed, then you have two spin. Okay. So the spin up and down will give you one state and another state, because of this coupling here. Okay, so this is produced by the spin conserving part of the Hamiltonian. Okay, so you get the split. When the M is big, then you get bigger. When the M is 0, then you have no splitting. Okay, that's why in the conduction band is M is equal to 0. That's why from this there's no splitting. In the valence band is big, 140 MeV. That 140 MeV is determined by this alpha parameter, and eventually is related to the atomic number of the atom. Is it okay? Any questions before we move on? Okay, so let's look at the band. Okay, so this is the calculation after you include the spin-orbit coupling. This is the band without spin-orbit coupling. So you just get one band. You can get something like that with the time binding model. This two band. I mean, the other band are not included in the time binding model. I think this is probably the DFT result. I don't quite know. Okay, but if you use the time binding model, you can reproduce the conduction band valence band. Okay, now once you include the spin orbit coupling, then you have the splitting. So you can see that the splitting in the valence conduction band is very small because it's m equal to 0. This part is big because it's m equal to 2. Okay, so let's talk about this Q value here. Okay, you can see it is big. So why? You can basically understand this by using the m number. Okay, so let's go back to look at this band. So this shows you the band. Okay, this dz square is m equal to 0. Okay, m equal to 0. So in this conduction band here is mainly m equal to 0. That's why the spin orbit coupling splitting is so small. And this blue one is m equal to plus and minus 2. So it's here. So that's why it's big. So let's look at the Q value. The Q value is here. Okay. So the Q value is blue, right? It corresponds to plus and minus 2. Okay. You see that it gradually changed. It becomes plus and minus 2. I mean, not as strong as this one. This one is basically 100% plus and minus 2 in our model. This one is not 100%. You can see the dots are not as big. Okay. So when you look at the spin orbit coupling, you see a sizable spin orbit coupling splitting, but not as big as this one. It's basically, you can explain this by m equal to 2 splitting. So you have a Q and negative Q. So you will expect Q and negative Q will flip. The spin direction will flip because time reversal. Everything you go to time reversal, the spin direction flip. You get exactly the same dispersion, but the spin direction will flip. Is that okay? So for the Q value, okay, let's talk about the value one by one. Okay. For the Q value, K is simple. K is we deal with this a lot. So basically, K is you have a very small splitting here. You have a very small. Okay, so you have a spin down. Yeah. Up. Up. Down. So you just change everything here. Okay, so this is on the K and negative K. So why there's a small splitting here? This small splitting is not due to the d orbit. The d orbit give you 0. Okay, is due to the I think I haven't checked it very carefully. I think it's due to the p orbit in Se atom. In Se atom. When you look at this result, so this is the p orbit of the S atom. Okay. We have not included the p orbit in our calculation. I want to make things simple. Okay, but the DFT calculation will include the orbit in the Se atom. So you can see that there is some p stay here. Okay, the p stay here. Not big, but it is there. Okay. Okay, so you look at the Se atom. Let's review a little bit this. This is the S atom or Se atom. They all have the p orbit, and the number here is 16. This is MO is 42. So you know it increases like the power of 4, right? So the S p orbit is significantly smaller. Okay, you just go back to check the formula for spin orbit coupling, but is there. Okay, you have the p orbit. Yeah, so this will give you a small spin orbit coupling. So for MOS2 and for MOS2, the conduction band splitting is quite small. It's quite small. Okay. Okay. So I mean, this is the result that people calculate for the K orbit for the conduction band. Like Kc means conduction band K value. The majority orbit is the M means the transition metal. Okay, it's dz squared. The minority is the X means the chalcogen. Yeah, people use mx2 to represent them. X, they have the px and pz orbit. Px and pz orbit, and this one will give you spin orbit coupling. So there's a minor splitting in conduction band that is quite small. Okay, usually it's not. I mean, it's much more difficult to see the effect than the conduction band. Okay. So, but for the valence band, these are the m equal to plus and minus 2. This majority orbit, minority. You also have the p orbit. Okay, you see from here, you still have some. Okay, but since you already have a big spin orbit coupling splitting here, so this minor contribution doesn't seem to be significant. Okay, so now let's look at the Q value. The Q value, you look at the figure, you already know majority is still the d orbit in the transition metal atom. Okay, these two. Okay, and then there's a minority. You see, there's also a p here. Okay, this is the Q value. So you only have the dz square. Like you have a little bit yellow, red dot here, red circle here, little bit. Okay, the minority, and then you have the transition metal. So chalcogen, X, Y, Z, they're all there. Okay, so totally you will have some splitting. So eventually you produce a spin orbit coupling like this. So if you go to the opposite value, there's totally 6Q value. There's totally 6Q value. So these are the K, negative K, 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 negative K. So the Q value is somewhere here. Somewhere here. Let's say you have a Q. Let me change the minus sign to be here. Okay, so this is Q. So this will be negative Q. Okay. Then here the band will be something like this. Let me zoom in and enjoy it. So you have a band like this. You have a band like this. And then you have spin down, spin up. Okay, you have a spin up is splitting. Then you get the same thing here. You get the same thing here. Okay, but then the spin will be flipped. Okay, because they're related at time reversal symmetry. But since the system has no inversion symmetry, each band only have one spin. Okay, and this spin orbit coupling is contributed mainly by the d orbit, with some contribution from the p orbit. Okay, so that is the property in Q value. Is okay?
Just go back to the 4 points about the contribution.
Okay, now let's look at the gamma value. The gamma value is simple because it's at the center. Okay, so let's go back. Okay, so this is time reversal symmetry. Yeah. Copy. So for gamma value, for gamma value. So for gamma value, this K is equal to 0. This K is equal to 0. And of course, this negative k is also 0. So in gamma valley, you always have this spin degeneracy. So the gamma valley will be.
You switch to that.
Sorry. Okay. Gamma valley. So this one will flip the spin time reversal. You buy a. You flip the spin by time reversal symmetry. You also flip the k, but is at 0. So negative k is still 0. So that means here you will have a spin-orbit coupling. You have both spin and the same. But once you go away from it, then they will start to split. Once you go away, then they will start to split, and the splitting direction will be let's say like this, and then on the other one it will be go up. Okay, once you go away, then you follow the time reversal symmetry. The spin is flipped. Only in the middle point, then it's the same. Okay, spin up and spin down is the same, and the spin-orbit coupling will not leave the degeneracy, because this degeneracy is protected by time reversal symmetry. Unless your perturbation break the time reversal symmetry, otherwise you will never leave the degeneracy. So the only way you can split the gamma point is to apply magnetic field. You use the Zeeman shift to split them. Otherwise, even if you include the spin-orbit coupling, because spin-orbit coupling does not break the time reversal symmetry. So this degeneracy is robust. Is robust. As long as you have the time reversal symmetry, it stays there. Okay, so we went through the K valley, Q valley, gamma valley. Okay, so okay, so we still have some time. So let's talk about the spin. Another thing I want to highlight is that the Q valley, because it has some p orbit contribution, this p orbit contribution is in the SE atom. So they're localizing in the, like you have a like a layer like this. Okay, so if you go to bilayer, then like for the K valley, they're all localized in the middle atom. So relatively speaking, the interlayer coupling is relatively weak. So if you go to different layer, the K valley band structure is similar. But for the Q valley, you have some contribution from the SE atom. So then they will touch each other. So they tend to have a stronger interlayer coupling. Of course, these are very like a simple, naive explanation. There are a lot of details, but overall, you can see the difference just from this basic consideration. Okay, so now let's consider the other term. Let's consider the other term of the spin-orbit coupling. Okay, this is the spin-orbit coupling term. So let's consider the other two. When we only consider the first term, the spin conserving term, when you only consider this term, the spin up and down, they're good quantum number. Okay, so this one, spin up and down, are good quantum number. You can say this state is spin up, that state is spin down. However, once you include this, spin up and down are no longer good quantum number. That means you can never say a spin is spin up 100% because spin up and down is not an eigenstate of this term. Okay, so once you include this term, you can never say this state is spin up 100%. Okay, you will have a mixture of the spin down. You will have a linear combination of spin up and spin down once you include this term, and that is actually very important for the dark exciton, because photon can never flip spin. You just remember, photon can never flip spin. If you have an exciton, like if you have two bands, this and this is down, this transition is forbidden. Like the lifetime is very long. Like if you let's talk about two level system. This is spin up, this is spin down. This lifetime is probably, I think, in the order of years. Yeah, it's longer than your lifetime. Yeah, if you have an electron with a spin up here, like two level system, you have an electron spin up here, it will almost never decay. Like very long lifetime. I don't quite know. I don't quite know. You need some new thing to couple the spin and couple these two states. For example, one example is the hyperfine structure in hydrogen atom. So basically, you have a hydrogen atom, and then you have a proton. Okay, the proton has two spin. Like the proton has spin up, and then the electron, like the proton have a spin, the electron has a spin. So the electron can have a triplet state and the singlet state because of the spin coupling. Like you have the spin coupling between the proton and electron. So the electron will have two states, like the triplet and the singlet. That does a very small splitting, like two spin interact very weakly. So they will have a splitting of about 21 wave number. So this one is very long lifetime, and people detect this as a signature of a hydrogen atom. They observe this signal from the galaxy. 21 sorry, not 21 wave number, that's my mistake. 21 centimeter wavelength, like it's a microwave emission, radio wave, microwave, radio wave. So that lifetime is very long. Like you jump up to here, it takes a long time to flip the spin. Okay, so everything that you see in optics, this so-called spin forbidden dark exciton, can give you a line in your data. They are all due to spin orbit coupling. They are all due to this spin flipping term. Okay, you can never I mean, you will measure the lifetime of dark exciton, right? It's not in the order of years, right? It's a nanosecond in that range. Okay, so not like this. So okay, so what is this? How do we deal with it? So first, you use a Hamiltonian, the original 3x3 matrix or whatever DFT. I think you need more than 3x3. Okay, so look at this band. We're going to include, you're going to include the green band here. Normally, we don't need to deal with them. But the spin-orbit coupling somehow allow the green band to participate. So I'm going to use three names, C1, C, C prime, and V. Okay, so I'm going to write it in this way. You have two bands. Okay, I call it C, C prime, and then a V. So no spin-orbit coupling. Spin-orbit coupling. So then you will have the spin up and you have a spin up and spin down. They all degenerate. Okay, so we're fine with it. So once you have the spin, conserving spin-orbit coupling, like this term alpha, LZ, LZ. Okay, once you have this term, then you're going to split them. You're going to split them. Okay, I don't want to add the color. Okay, just I just make it simple then. Okay, you just split it. Okay, now if you have the spin flipping spin-orbit coupling, that means you have this thing once you have this, then you treat this as a perturbation. Okay, so this is C minus C plus C prime minus C prime. Okay. Okay, so this state will be coupled to what state? Will be coupled to this state. Why? Because they flip. Okay, and then this is M equal to plus and minus 1. This M plus minus 2. Okay, so this minus 2. This two will not be coupled. Why? Because they have the same M. In order to make this term happen, for example, spin, you have a M equal to 2, and the S spin up. Okay, once you have this state, it will become what? The spin will go down, and then the M will become it need to be 1. Okay, so this will become 2. So that means L plus L minus, you couple to L M equal to 2 spin down. This will be finite. Okay, you get the idea? So if you have M equal to 2 spin up, let's say this one, and then you have also M equal to 2 spin down, like this state, this one will give you 0. You get it? Because you have the same M. Okay, when this sorry is 1 1 need to be 1 1. Okay, like this two will never couple. I mean, you can do the same thing, but for M equal to 2, for M equal to 2, then you need to lower it, and then the S need to be plus, so this will be down. Okay, so if this is M equal to 2 and spin up, so this will be 0. I mean, you can easily consider a few examples. You can easily consider a few examples. like when you add this spin flipping term, what kind of state will be coupled together? You just use the number. So that's why we need to include the green band. Like this green band, we need to include because this is m equal to plus or minus 1. It will be coupled to this lower band due to the spin flipping term. Okay, so we use C prime. Okay, so experimentally we do not measure the optical response from this band. We'll measure the optical response of the lower band, but this lower band will include some mixture from the upper band. Okay, so the perturbation is this. Okay, so this is the new state. Originally, we are going to use a first order perturbation. So you know that initially you have a new eigenstate of spin down, okay, in the conduction band, but after you include in spin conserving spin orbit coupling, so this one will become a new state. We still use the same symbol, but I'm going to add a bar here to show that it is a renormalized state. Okay, will become see this, and then we'll plus. You just apply what you learn in perturbation theory. We'll get mixed with the spin up prime. Okay, spin up. This is m. This is m equal to this move down, so you need to go up. So this you need to -1. So this will be -2. Okay, so you flip the spin down and increase the m to 1. Okay. Sorry, this sorry, this will be 2. This will be 1. Okay, this will be 1. Then you have the C minus. Let me just okay. So then you have a alpha S minus plus, and then C, and then you have the energy of C minus energy of C plus. I mean, you remember the equation, right? For perturbation. I mean, in principle, you need to sum over all states. Okay, you need to sum over all the state that with the finite matrix element. But the other states are far away. Because the closest one you can find to have a finite matrix element is this one. Is this one. You need m equal to 1 to have the finite matrix element. The closest one with the m equal to 1 is this one. Or the next one will be here. But once you are going far away, then this energy denominator will be big. So they will become minor. So for simplicity, we just use one term. We'll just use one term. Okay, so this will be the renormalized state. Okay, is okay? So what is the matrix element for your dark exciton? Your dark exciton is basically from this one, this state. Sorry, okay, let's consider emission then. Okay, emission. Then we'll have a P. Okay, this is the dipole. And then you're going to have a V. Your V is going to have an opposite spin. I mean dark, right? Dark. So this V is this. So this is your dark exciton, a matrix element. So you can see that these two spins are opposite. You almost never get any coupling if you have an opposite spin, if you just consider a photon effect. However, in your experiment, you see some light emission from from diexciton, right? Why? Because of this. Because of this. So this one is what? So you're going to have actually this whole thing. This whole thing is going to include here. Okay, so include this whole thing. Then you're gonna separate them. And then this thing. Okay. Okay, this term will be 0 because these are pure spin states, like the pure spin, 100% spin up, 100% spin down. You get 0. Okay, but this term you actually have the same spin. You actually have the same spin. Okay, so this term, I mean let me see, this one you can move this outside. I mean, it's a number. Okay, you can move this outside. Okay, so here you see here, you are actually using the matrix element of an upper band. This one has m equal to 1. This one have m equal to oh yeah, sorry, I'm making mistake all the way along. It's m equal to 0. Okay, so this is the conduction band. Okay, sorry, this is conduction band. This is a conduction band. So is a conduction band is 0. Okay, so I need to change. Okay, sorry, I didn't prepare very well. So this is 0. You lower the spin, so this is 1. Wait, this is 0. This is the original one. So you lower the spin. Okay, so then this one need to be -1. Okay, so this is 0. This is -1. Okay, -1. This is -1. So this is the conduction band. This will be -2. Okay, so you can see that it just happened that they will just couple very well. Why it is I think either plus or -2 is okay. Okay, because this one also need to be finite, but these two have opposite parity. Okay, and this one has also odd parity. So eventually, this is a finite matrix element. Okay, this is finite matrix element. So here, the interesting thing is this: you actually make use of the upper band, which you normally don't draw. I mean, when you draw the band structure of MOS2, you just draw the lower conduction band, right? You just draw this part, right? This is what you draw in your analysis. You usually will not notice the upper band there. However, once you consider the diexciton, you need to consider upper band because it is coupled to the lower band, so that you have the spin up and spin up, both of them are spin up to produce a finite oscillator string for the diexciton. Okay, and here this energy separation is important. The bigger the separation is, the smaller this one will be. Okay, the smaller one this will be. When you go to the conduction band, let me see, the conduction band, you also need to consider that, but this one is somewhat further away. I mean, it's still here. It's something like this. This one will also flip the spin of the valence band. So why is the valence band spin is like I would say so much pure? Like the conduction band spin is not very pure because of this spin flipping term, and also the two spin like the separation is small. Okay, the spin up and spin down separation is small due to the lack of spin orbit coupling for the spin conserving term, and also you have a lot of spin flipping mechanism due to this upper band here. When you go to the conduction band, valence band is different. First, the spin conserving term already split it quite far away, 140 millieV over MOS2. And then the spin flipping term is far away. Okay, I mean, it's a little bit far away than here. And also the weighting is small. I mean, this is a big green symbol. This is a smaller green symbol. So it's a somewhat little bit further away, and the weighting is smaller. A lot of them comes from the P, but the P is on another atom, right? So you can imagine that the spin flipping mechanism will be weaker. So overall, when you consider the spin property in the valence band, overall is higher quality, like well separated. Like that's why when you see Fang Wang's paper, and they have an ultra long spin lifetime, right? Valley lifetime, right? I mean, it's in the valence band. Because the splitting is larger, that is I think the major reason, and the spin flipping thing are also like significantly weaker, I think. Yeah, I don't know exactly the number how much weaker, but overall, I don't know how much is related to that lifetime thing. But you can imagine qualitatively that everything related to spin and valley will be of higher quality in the valence band. Okay. So, what else? And also, we haven't talked about it yet. The selection rules will follow this. Will follow this. This will give you the selection rule, like the polarization of the light. We haven't talked. I mean, later after I talk about group theory, we can go back to revisit this problem. For the bright exciton, it gives you circularly polarized light, but for the dark exciton, give you linearly polarized light. That polarization is controlled by this matrix element. And if you calculate this matrix element, the orbit that you need to consider will be the m-1 orbit and m-2. Now, you need to know that these two combination, like you have a C, this with a V, this. Now, this will be the bright exciton. Okay. So I just want to point out the difference. Now this is the dark one. The dark one. The dark one. This is the bright one. Now for the bright one, there's no prime. It's the lowest state. So this is m equal to 0. This is m equal to this will be +2. Okay. Because they +2 means -1, right? Let me see. I think either way is okay. Either plus or -2, I think it's fine. Okay. Or -2. Okay, the main difference is that this is a different state. You need to understand why dark exciton and bright exciton, they have different selection rules. The main reason is because the matrix element are contributed by different orbits. For the bright one, is contributed by the m equal to 0 orbit. Okay, this orbit. But for this one, is contributed by the m-1 orbit. The m-1 orbit is which one? Let me see. M-1 orbit is this one. So this is the dyz and dxz, and this one is dxy dx. Okay, so the valence band is basically this orbit. For bright exciton, you're dealing with this dz square orbit. For the dark exciton, you're dealing with this. After we talk about group theory, when you learn it, then I can show you the selection rules that they have. Because of this different symmetry property, this will give you circular polarized light. This will give you linearly polarized light. But the underlying reason is because they correspond to different orbits. And this is something that actually I didn't know before until I wrote the paper with Dr. Chang that he explained to me. Because before I was actually quite like puzzled. Because when people draw the band structure, they usually just draw this part. I just don't understand why the bright exciton, dark exciton. I mean, there are two things that I don't quite understand. Why the spin forbidden one can emit light? Like what is making the spin flip? Okay. Second is, why would they follow a different selection rule? Or later, Dr. Chang explained to me, oh, okay, that is the reason. Because of the spin-orbit coupling, there's a spin flipping term that just caused this to happen. And we actually need to consider a higher band. So let me see. This is the work that we did in Erfu's paper. So this paper in Physical Review Research, if you're interested, you can read it. So this one, we talk about the bright exciton emission, the dark exciton emission with a different polarization. We also talk about the phonon replica. Once you add the phonon replica, then you have a new perturbation that will give you a new selection rule. I think after we talk about group theory, we can go back to visit these three cases. Then there's a lot of information in the supplementary material, particularly this part on group theory of bright exciton, dark exciton, and phonon replica. So what I told you today is part of this section. So I mean, I draw this like no spin-orbit coupling. I will explain this. Spin conserving spin-orbit coupling. We have this. You have bright exciton, dark exciton, and then you have a spin flipping second spin-orbit coupling. This is the C prime band. This one, I draw an arrow here, means these two are coupled. Then you have the photon with the PZ linear polarization. Now this dark exciton, I draw a dashed line, means it is forbidden. Once I draw a solid line, means it is allowed. And then you have the electron phonon coupling that will allow this upper band and these two will couple together. When you have this electron phonon coupling, and this will give you a new selection rule. I think the whole thing is actually interesting. So these are the orbits that we consider, and these are some character property from the group theory that I mean, after we talk about group theory, I can go back to revisit this table. And these are the orbit. This C prime is this orbit. This C is this orbit. V is this orbit. These are the character property of this related to symmetry. Okay, so what I show you is this part. I said according to the first perturbation, first order perturbation theory, the spin flipping spin-orbit coupling, we change this band, modify this band to this, and then this is the part. Then I have the selection rules here. Okay, so basically the information, some of the information I included here. If you're interested, you can read it and have more understanding. So okay. Any questions? Fahima, you have any questions? Okay, any questions? Okay, if no, then we'll end the lecture here. Thank you very much.